All right, welcome everyone to the wonderful world of 1.5, the limit of a function. In this video, we're going to be taking a graphical approach to finding limits of functions. So the objectives, right? I need to tell you a little bit about what is this thing, the limit, right? So we're going to try to gain an intuitive idea for the limit of a function. And then we're going to practice finding some limits. And there's going to be different kinds, two-sided, a left-hand limit, a right-hand limit. And we're going to do these for specific piecewise defined functions given algebraically or graphically. That's a mouthful. It doesn't really mean much right now. I'll show you what it means here in a second. But before we get to that, let me do some motivation, right? So last time in 1.4, we looked at a graph like this, right? And our goal was to try to find, maybe this tangent line, specifically the slope of this tangent line. And we talked a little bit about approximations, and we had this idea, right? So this is the tangent line at 6, I guess, is what I'm interested in. And the idea was that we were going to use the secant line, right? So the secant line, we could take one of our points and pin it right here at 6. And then the other point, right, that if we let it be close to 6, I'm going to start moving this and making it close to 6. So here's 5.9, very close indeed. We can see that these slopes of the two lines are very close to one another. In fact, the green line and the purple line, you can barely tell them apart right here. However, when it's equal to 6 exactly, the claim is that it breaks down. So we need to develop a notion for close to a number, but not equal to a number. So in this case, right, when it's equal to 6, it all breaks down, right? You don't have, this average rate of change doesn't make any sense. However, when it's just close to 6, it does make sense, right? And we can actually see that these slopes are indeed close to one another. So we need to develop something that talks about what happens when you're close to a value, but not equal to it. And that is a limit. So, limits. Let me give you kind of the more formal definition here, and then we can start sketching and whatnot. So suppose we have a nice function f of x, and it's defined near the number a. Then we can write the following. So this is notation. This is the limit as x approaches a of our function f of x is equal to some value, some real number, L, if we can force the values of f of x as close as we'd like to L by requiring x to be sufficiently close but not equal to the value a. Oh my goodness, what does this mean, right? It seems like a lot of craziness. Let me show you. In fact, so if we go down here and if you click on this link right here, it's going to take you to another kind of app that we're going to be playing with today. So the 1.5 limit stuff. Okay, so let me show you here. We're going to be interested around this function. So it's a nice piecewise defined function. You see it has lots of pieces essentially. And we're going to be interested around this value -1. So if I asked you what is f of -1, well, there's a hole there, right? It doesn't make sense to say what is the function's value at -1. Again, there's a hole. But I can talk about what the function, kind of approaches, what it's near to when x is near -1. So that is the idea behind a limit. So for instance, I have all these kind of little things, and you can play around with them and see what they do. But this one kind of changes those green points there. So those green points, you can imagine that you're riding this function, and you're getting closer and closer to -1. You can see that these green points seem to be getting closer and closer to each other and are going to a specific height, right? Functions usually spit out heights. And so you can see that they're getting closer and closer to the value 2.5. Now, again, it doesn't actually hit 2.5 because there's a hole there, but you can get extremely close to 2.5. And again, this is the idea behind the limit. So now let's go back and look at this one more time in the context of our problem to try to make a little bit more sense of it. That number that we were approaching was -1, right? We were trying to get really close to -1. It's defined near -1, but not at -1. So if I said f of -1, it doesn't make sense. However, we can force, the claim is the limit is 2.5. It's getting closer and closer to 2.5. And we can get f of x as close to 2.5 as we'd like, right? Let me skip back here one more time, right? The function's very, very close to 2.5, around -1. Right? It's very, very close to 2.5 indeed. if we require x to be really close to a, or in our case, -1. Okay, so just so that way when we kind of look back on this a little bit later, I'm going to go ahead and draw a static picture. So here's A. Static pictures are nice sometimes, but I really like to be able to play with, the functions and whatnot. Here's our function f of x, and the claim is if we approach A, not equal to A, but we approach it. And notice we can approach from the left or from the right, kind of from the smaller values or from the bigger values, that they get closer and closer to this height, this y value of L. So this L is always a y value, something that the function gets very, very close to when you're nearby A. Now, sometimes we can't talk about a limit, and I'll get into that here in just a second. Kind of approaching from either the left or the right, it turns out it doesn't always exist. What's a little safer is talking about a left-hand limit. A left-hand limit, or down here, a right-hand limit. So let me show you the notation for this. This is the limit as x approaches A of f of x is equal to L. So very, very similar to this up above. The only difference is that we're going to do a little minus sign here in the superscript of A. Right? So this is going to mean we're approaching from the left. And so this has a lot of the same definition as we have above. We're getting very, very close to A. The only, I guess, the main difference here is that we're approaching from the left, right? It's a left-hand limit, so it's not equal to A, it's less than A, right? We're approaching from the left. This would be this one right here, approaching from the left. Likewise, we can talk about a right-hand limit. It has a lot of the same notation, except now for the superscript for A, we have a plus sign to denote that we're coming from the big, like positive infinity essentially, and that this would be kind of writing the function here, again, from the right-hand limit. And in this case, f of x still gets very, very close to L by requiring x to be close to A, but greater than A. So this one's just strictly less than A, this one's strictly greater than A. And actually, let me go back to my app one more time here and show you a case where you would really want to talk about the left-hand limit and the right-hand limit. And it's actually over here at 2. So I'm going to go ahead and change this, and we're going to be very interested around the value of 2. Let me back out here in a second. Okay, and so in this case, we can play around with this, but as the distance gets smaller, you can see that these two green points, they're not getting close to each other, which is a little bit strange. So I actually built in a way that we can turn off one of these points. So for instance, if I want to turn off the right-hand limits, let's just make that 0. And now you can see I only have one green point. This is the left-hand limit. So we're approaching the x value 2 from the left. There we go. Oh, oops. Oh, darn it. I touched the wrong one. I wanted to play with distance. There we go. So we're getting closer and closer to the value 2. And notice that if we're approaching from the left, it seems like the height here is getting closer and closer to 1. So we'd say the left-hand limit is 1 in this case. Now let's go ahead and turn on the right-hand limit. So the right-hand limit, as we approach from the right, bigger values than 2. As we approach from the right, bigger values than 2. In this case, the right-hand limit seems to be getting closer and closer to -2. -2. So let me go ahead again. I want to draw a static picture just so that we have it in our notes. So maybe here's the function's value. Oops, that looks a little too much like a closed dot. There we go. So here's our function in this case. And then for the left-hand limit, we want to approach from the left. Right? So if I'm writing this function from the left, our limit, our left-hand limit, would be this y value right here. Now, using the magics of video, let me go ahead and make another graph up here. And you can see that as we approach from the right, as we approach A from the right, the function's value is getting closer and closer to this height. So in this case, the left-hand limit and the right-hand limit are not equal to one another. And so if you were to come back here and try to ask for, okay, what is the two-sided limit right? What is just the regular old limit right here? The claim is, well, you have to write down two different numbers. And so when you have to do something like this, the claim is that it does not exist. So that's what the kind of this theorem here is about. It says that the two-sided limit as x approaches a, of f of x is equal to some nice real number L if and only if the left-hand limit and the right-hand limit agree and are equal to L themselves. So you need the left-hand limit to equal L, and you need the right-hand limit to equal L. And when that happens, when they both approach the same thing, that's when the two-sided limit exists. Let me really hit this home with an example here. So here's kind of a classic example. It could show up in on homework, quizzes, exams, all that sort of stuff. So our function is given to us by some graph right here, and we're asked a bunch of limit questions. So the first one, we're approaching 2 from the left, right? So 2 from the left, this little minus sign up here, kind of above the 2, means that we're approaching from the left. So I'm approaching 2 from the left. So this means I'm smaller than 2. Notice we have a dot here, actually at, when x is equal to 2, we actually have a dot here. But the limit doesn't care at all about the function's value. It only cares about when it's close to 2, but less than it, right? And so when it's close to 2, but less than it, it does seem to be getting closer and closer to the height of 3. Which just coincidentally happens to be where this closed dot is. But as we move on to b here, if we approach 2 from the right, so if we're going here, we're approaching from the right, then it's getting closer and closer to the y value of 1. And notice this does not have the closed dot. Okay. However, if you were to talk about the two-sided limit now for part C, what is the two-sided limit? Well, these don't agree with each other, right? These are two different values. So in this case, we usually write DNE for does not exist. So the limit does not exist. The left-hand limit and the right-hand limit are not equal to one another, right? If they were equal to each other, then the two-sided limit would be whatever that was. But because they're not equal, the claim is the limit does not exist. On the other hand, finding the two-sided limit of 4 works, right? So here's x approaching 4. I can go from the left and from the right, and they both seem to be getting closer and closer to the same y value. That y value happens to be 4. So in this case, the two-sided limit does exist. It's equal to 4. And then here's just a little bit of reminder of algebra days. Right, so f of 2 is, okay, what is the function's value at 2? So now you're actually looking for the closed dot. This is equal to 3. Again, remember, the limits don't care all about the function's value. But every once in a while you can, bring up f of 2, or in this case, f of 4. So if I go to 4 and I look for where is the closed dot, there isn't one, right? So in this case, we would again say does not exist, right? The function's value doesn't exist at 4. Okay, one more problem, then we're ready for a break. What happens if a function is not given to you graphically, right? So I promised up here to make more sense, the second objective, find limits, two-sided left and right, for a piecewise defined function given graphically, check. What if it's given to you algebraically? Well, that's what this one is all about here. So here we just have an equation, right? A piecewise defined equation, right? It behaves differently depending on its interval, right? So if x is less than 1, it behaves a certain way. If x is equal to 1, it behaves a certain way. If x is greater than 1, it behaves a certain way. So because this is, 1.5, this first video is that we're taking a graphical approach. The claim is we should be able to take this equation right here and turn it into a graph. And once we have a graph, well, then we can use the same technique as we did up here. So let me go ahead and turn this into a graph. Here's my coordinate axes. Oh, I did a horrible job with that. Let me go ahead and start over a little bit. Everything seems to be happening here around 1. I'm very interested in that. And this behaves differently, it behaves like x squared plus 4 if x is less than 1. It behaves like 0 on a certain interval. It behaves like 3 minus x on a certain interval. So let me go ahead and maybe try to sketch some of these. So I'm going to go ahead and try to sketch. I'll do the easy one first. 0 if x is equal to 1. So only when x is equal to 1, its height is 0. So it's right there on the x-axis. All right, let me do 3 minus x. So 3 minus x, I know that this, if I was to put it in, this is like point slope form or slope intercept form really. This would have a y-intercept of 3, 1, 2, 3, and it would have a slope of -1. So we'd have a point here, we'd have a point here, we'd have a point here, we'd have a point here. And you can go ahead and verify, right? So this is a straight line. If I plugged in 3, right? So here's 2, here's 3. If I was to plug in 3 for x, I would get 0 for y. Yes, that makes sense. So it's a nice straight line, so we get something like this. But hold on a second, right? This only works when x is greater than 1. So actually, I don't need this part of the function. Erase all that. Erase all that. And actually, at 1, I would technically need to erase this as well, right? So instead of a closed dot here, I'm going to try to just barely erase as much as I can and do an open dot. So right, when it's equal to 1, remember the function's value is 0. When it's just bigger than 1, okay, it's something. Then the graph go ahead and exists. That's not very good English, but okay. I hope you get what I mean. All right, one more here. X squared plus 4. Again, okay, I could plug in some values. So if I plugged in x equals 0, for instance, I would get out 4. If I plugged in x equals 1, I would get out 5. Or if I plugged in x equals -1, I would get out 5. Right, and so this is going to be looking like sort of a parabola looking deal here. There we go. But again, hold on a second. For our function, right, this only works when x is less than 1. So in fact, this graph right here doesn't actually exist. And when it's equal to 1, I need to erase this dot, and I put an open dot, something like that. Okay, so when you don't have a graph given to you, it takes a little bit more time, but we can draw out the graph. Now we can go ahead and evaluate these limits. So if I approach 1 from the left, so here I am writing my function, approaching 1 from the left, it seems to get closer and closer to the y value 5, right? So this height right here is at 5. 1, 2, 3, 4, 5. If I approach, however, from the right, approaching 1 from the right, the function's value seems to get closer and closer to 2. If I ask what is the two-sided limit as x approaches 1, well, we can see because these do not agree, 2 and 5 are not the same number, this does not exist. And then one more kind of interesting situation, I find students sometimes get tripped up on this. If we approach x equals 2, this is a two-sided limit, so if I was to approach 2 from either the left or the right, so sometimes when you draw it, right, it doesn't necessarily have this dot here, but it's getting very, very close to the y value 1. So it's getting close to this y value 1. Now it actually makes sense to ask what is f of 2. It also happens to be equal to 1. But again, the limit really cares about when you're close to 2 but not equal to it. All right, so that is equal to 1 in this case. Now I want to show you something kind of interesting. This is kind of a faster way to do this problem. I'll do it for part A and for part B here. But it takes a little bit more practice, and it's not a graphical approach. So, okay, if I was to plug in, right, so if I'm less than 1, let's think about this again. I'm approaching 1, I'm a little bit less than it. So then I'm up here on this first line, right, because I'm less than 1. To the left of 1 is less than it. All right, so I'm approaching 1. I'm trying to basically plug in 1. I can't plug in 1, but imagine plugging in something very, very close to 1. It might as well be 1. If you plugged in 1 here, 1 squared would be 1 plus 4. That would equal 5. Now again, technically you can't plug in 1. You'd have to think about plugging in like 0.9999 or something like this. If you plugged in 0.9999, when you squared it, again, it's going to be like 0.9 and change, right? It's going to be very, very close to 1. And when you add 4, that's going to be very, very close to 5. Likewise, over here, if we're approaching 1 from the right, From the right, that means bigger than 1. So we're kind of determined by this one right here, this last line. And so if you, again, you can't technically plug in 1, but what if you did, right? So if you plugged in 1, it'd be 3 minus 1 would be 2, right? So that, it makes sense. So 3 minus 1 is 2. Again, you can't technically plug in 1. You can plug in something bigger than 1 that's very close, to like 1.001, something like this. And so you would get something very, very close to 2, but just a little bit less than that. All right, so that's kind of a different approach. We're going to expand on this a lot more in 1.6, but that's another interesting idea as you try to do these problems. All right, I think that's it for this video. Take a break, stretch your legs, and I'll see you guys next time in our second video evaluating infinite limits numerically. See you then.